In this video, we are going to talk about a strategy called trig substitution, or in general, inverse substitution. We're going to use trig functions to make our substitutions, but this strategy would work for any function that we want to use as long as we can guarantee it has an inverse. So let's take a look at some very specific types of roots that are going to be useful to put in a trig substitution. So which types of roots are we looking at? Well, we are looking at roots of the form the square root of a squared minus x squared, square root of a squared plus x squared, or the square root of x squared minus a squared. Now, there's a little star right here, and that's because we want to look at these roots when they cannot be done with a u substitution. Sometimes we see roots of that form and we can use a u substitution. As we build our integration strategies, we don't want to forget that we have those previous integration strategies, right? We're going to continue to add tools and techniques into our toolbox of integration strategies, but we don't want to forget that we have those original integration strategies that we've been working with for quite a while. So let's take a look at these two integrals that we have right here. We have the integral, they both have the same square root. They have the square root of 4 minus x squared, square root of 4 minus x squared in them. But they are done using two different types of strategies because the first one can be done with a u sub, and the second one is one that we're going to have to use, and I'm going to use it to illustrate why we might want a new strategy. So this is going to be using our new trig sub strategy. So we're going to do these two integrals and talk about them. But notice they both have that same root, but we want to check before we get into trig substitution or substitution, inverse substitution, we want to check to see if we can just do a simple u substitution. So we do always want to remember that we have u substitution. Notice on this first integral, as we were talking about just 1 second ago, that we could use a u substitution. So if we let u be 4 minus x squared, then du is negative 2x dx. We can solve for the x dx because I see that I have an x and a dx, of course, in my integral. So if I solve for x dx so that I can make the substitution, I find that minus 1/2 du equals x dx. And I can make those direct substitutions. So this becomes 1 over u to the 1/2, or the square root of u. The x and the dx I'm now going to replace with a minus 1/2 du. And look at that, since I can make the u substitution, even though this is of the form, the square root of a squared minus x squared, which we're going to talk about a new strategy for dealing with something of that form, even though it's of that form, I want to use my previous strategy, my u substitution, because this is a simple u sub problem, becomes negative 1/2 u to the negative integral of u to the negative 1/2 du. When I integrate, I get u to the positive 1/2 divided by 1/2, but when we divide by 1/2, that's the same as multiplying by 2 over 1, plus an integration constant, and I end up with negative u to the 1/2 plus c. Plug my u back in, and that becomes the square root, because it's also to the 1/2, of 4 minus x squared plus c. And that is my integral. Just a quick review and reminder that if we can use a u substitution, if we can use our basic integration strategies, our u substitution, our integration by parts for that matter, that we want to try one of those strategies that we already have in our toolbox. We want to kind of run through the list of strategies we have, and if we can apply one of those strategies, we want to do so. Now, we cannot, let's try to get these both on the screen at the same time. This same u substitution does not work for this problem, and you can see that right here. If I let that be my u, this would be u to the 1/2 on the bottom. I have an x squared over 1. My dx would be a negative 1/2 du, and I'd still have this x squared. Well, I could play around with that x squared, that we could solve for x squared. We could maybe substitute in right there a 4 minus u for x squared. But then we have the u to the 1/2, and we have the 1 on the top, and if we distribute, we still end up with an integral of 1 over 4u to the 1/2 minus u to the 3/2. We've got that minus 1/2 and that du, and that's not really getting us anywhere. We're not in a position here where we can integrate. We have made this substitution, but we are still unable to integrate it in its current form because we have more than one term in the denominator. We got those roots. So even though we could make the substitution, it didn't turn into something that I was able to integrate. So That substitution doesn't work. So what we're going to do instead is this little process called trig substitution. We're going to use a substitution on x that is a very strategic trig function so that things will simplify and cancel. And so I want you just to watch how I do this first one, and then I'll write up the formal steps and talk about the process for an integral that has an a squared minus x squared in them. So on this one, since we can't use that u substitution, what if we do what we call a trig sub? What if I let x equal 2 times the sine of theta? Now, why would I do that? Well, I'm going to use that substitution. I am going to have to be a little bit careful here. I'm going to say where theta is in the interval from negative pi over 2 to pi over 2. Now that comes from the fact that I want this trig function that I'm going to make this substitution. I want to be able to undo the substitution I'm putting in here. And so the reason I'm restricting sine from negative pi over 2 to pi over 2 is because I want it to have an inverse. This is so this function has an inverse. So that's why I'm doing it. I want to make sure that this function actually has an inverse. If I restrict it from negative pi over 2 to pi over 2, it becomes 1 to 1 and will have an inverse. And that is the standard restriction on the sine function when we talk about its inverse. So going back to just trig functions and their inverses, trig functions themselves are not 1 to 1, so we restrict them. On a restricted domain, they are 1 to 1, and then we can create or talk about their inverses, define their inverses. So this is the standard restriction on the sine function for when we create an inverse. So we're taking our normal sine function, in this case it's 2 sine, but we take our normal sine function, it goes boop, like that, and we say, let's look at it just from negative pi over 2 to pi over 2, just on this highlighted region right there. And on that highlighted region, it is a 1-to-1 function. Therefore, it will have an inverse. Okay, so if I do that, if I let x be equal to 2 sine of theta, then I can plug that in for the x's. So where I have the two x's, I can plug that in. Now the thing is that's going to happen here is this integral is going to become in terms of theta. So this will become 2 sine of theta squared, square root of 4 minus 2 sine of theta squared, and then my dx is still sitting right there. And now I have a funky, let's circle that because we're going to have to replace that. Now I have kind of a funky integral because I've got, my integral has gone from being in terms of x to being in terms of this new variable theta that we're defining. But we're integrating with respect to x. So we have to also switch our differential. So I'm going to erase that because I have to also make a substitution on the differential. So here I have x equals 2 sine of theta. Well, then the derivative of x with respect to theta would be 2 cosine of theta. Take the derivative, separate the differential, and dx is 2 cosine of theta d theta. And I can make that substitution for dx. So dx is going to become 2 cosine of theta d theta. So I'm making substitutions just like I do with a u substitution. I'm making substitutions here, but they're slightly different substitutions. I'm replacing x instead of picking a function within the integral to define as u. I'm replacing x with this trig function. And why would I want to do that? Well, watch what happens. Watch what happens under this root. In particular, the rest of it will simplify as well, but take a look at what happens right here. It's this root that we're focused on. What is going to happen here? Well, let's see what happens with the trig function there. So this becomes 1 over, this becomes 4 sine squared of theta. This square root becomes 4 minus 4 sine squared of theta. We still have the 2 cosine of theta right there, d theta. And notice right here in that 4 minus 4 sine squared of theta, that becomes 4, factor out the common factor of 4, 1 minus the sine squared of theta. But remember, quick little recall over here, sine squared of theta plus cosine squared of theta equals 1. And so cosine squared of theta equals 1 minus the sine squared of theta. And if that's the case, this right here is just the cosine squared of theta. So this becomes the integral of 1 over 4 sine squared of theta times the square root of 4 times cosine squared of theta. We still have this 2 cosine of theta hanging out up here. I guess we could have moved that into the numerator. But there it is. And notice we have 4 times the cosine squared of theta. Notice by making that substitution, I want to try to get it all on the screen. Notice by making that substitution where I have that highlight, notice right when I made that substitution, it allowed me to simplify that all the way down into a perfect square, and it's under a square root. So when we take the square root of a perfect square, that is simply going to become, I'm going to go ahead and move that 2 cosine of theta into the top. I keep leaving it off to the side. We can move it up top. We still have the 4 sine squared. I haven't done anything with those other terms. I'm just dealing with that square root. That now becomes just times 2 times the absolute value of the cosine of theta right there. Now, it is in absolute value, but the absolute value of the cosine of theta is simply equal to the cosine of theta when theta is between negative pi over 2 and pi over 2. Remember, we have that restriction. Our function that we substituted right here, in order to make the substitution, we had to guarantee it was 1 to 1 up there at the top. And so since we did that restriction to make it 1 to 1, when I took the square root and got the cosine, if we think about just the cosine curve, remember negative pi over 2 to pi over 2, you're talking about being in the first or the fourth quadrant, or you could think about the graph of the cosine, however you want to think about it, but it is definitely positive. Right? It's the absolute value. It's just equal to itself on that. It is positive. So I can drop the absolute value. And this is actually exactly equal to 2 cosine of theta over 4 sine squared of theta times 2 cosine of theta d theta. And look at that. So I was able to drop that absolute value right there. But it's not insignificant. We do need to guarantee that when we have the absolute value of something that we can drop it if it's always positive. Now this reduces, and look at what my integral has become. It's become the integral of 1 over 4 sine squared of theta d theta, but that's just 1/4 the integral of the cosecant squared of theta d theta, and that is just negative cotangent. The integral of the cosecant squared is negative cotangent, and so that's negative 1/4 cotangent of theta plus c. And so my integral has become negative 1/4 cotangent of theta plus c. Now I would love to circle it and say I'm done, but I'm actually not done because my original integral was in terms of x. Now I've got another page that I'm going to share with you in just a second off to the side. Let me scooch that out of the way. Okay, so I've got it all on the screen here. And remember, I rewrote it so we can zoom in on it up here on the right. But what we did right here was we strategically picked a function, a trig function, to plug in for x. When we did so, we had to make sure we restricted the domain on the trig function so that we could undo that process, essentially, because we needed to have an inverse in order to do that. So we restricted our theta between negative pi over 2 to pi over 2. We made the substitution. It worked out really convenient, and lots of stuff canceled, and we reduced down to something we could integrate. We've got the integral of we've got the integral of the function we started with, 1 over x squared times the square root of 4 minus x squared. That integral becomes negative 1/4 cotangent of theta. The problem is we have a theta and we need it to be in terms of x. So how do we do that, right? We're integrating in terms of x, but we've got an answer in terms of theta. So what we have to do is we have to utilize how we defined x was equal to 2 sine of theta. How did we create that relationship so that we can get back to it? And this is where we use the inverse property. So it turns out here, if I divide both sides by 2, that the sine of theta is equal to x over 2. So theta is actually the inverse sine. It's the angle whose sine is x over 2, right? And in order to do that, we had to have that restriction on the domain. This was where theta was in the interval from negative pi over 2 to pi over 2. So now, in order to write this in terms of x, we have a few choices. We can use identities and properties of trig functions, but I like to use a triangle. And I'm going to draw my triangle that has an angle somewhere between negative pi over 2 and pi over 2. So I'm going to draw what's called a reference triangle. I'm going to actually draw it right here. The reference triangle, and it is going to be because it's between positive pi over 2 and negative pi over 2. So it's going to be somewhere in one of these two quadrants. And when I draw it, I'm going to think about the fact that my angle, the sine of my angle, is a ratio of the opposite side to the hypotenuse. So when I draw this triangle, I'm going to draw the triangle either in the first or the fourth quadrant. And the opposite side I'm going to label with x, and the hypotenuse side I'm going to label with 2. Now this triangle could also have been drawn here if the x was negative. I could have drawn the triangle here. That would have been, we could have drawn it just like that, either way. And this side, the third side of that triangle, we can find using the Pythagorean theorem. So the third side of that triangle using the Pythagorean theorem has to be the hypotenuse squared minus x squared and the square root. Now I'm going to get rid of, we could have drawn it there, I was doing that for visualization, but I'm going to get rid of that other triangle. So we're just looking at this reference here. Regardless of which quadrant I drew my triangle in, this side of the triangle is a positive square root of 4 minus x squared. Now this is my theta. So this triangle, regardless of which side it's drawn in, when I use that triangle, I can use that to find the ratio, the trig ratio of any of the trig functions. So the cotangent, for example, the cotangent of this angle, given this reference triangle, the cotangent is always the adjacent side over the opposite side in the right triangle. So the adjacent side is the square root of 4 minus x squared, and the opposite side is x. So I can use that to rewrite my answer, which is now in theta. I can use my reference triangle to write my answer as negative 1/4. Now the cotangent is the square root of 4 minus x squared over x plus c. And that is my answer. I guess we could simplify that just a little bit. Minus the square root of 4 minus x squared over 4x plus c is my answer using my reference triangle to go from my answer in terms of theta to my answer in terms of x. And that is this new process that we're going to use called trig substitution. It's a new tool. If we cannot make a substitution, a u substitution, in order to integrate our problem, we can try using a trig substitution. And trig substitutions are good for roots of the form a squared minus x squared. I'm going to scooch this over here and talk about this strategy now. They're especially useful for roots of the form a squared minus x squared, like the one we just did, roots of the form a squared plus x squared, and roots of the form x squared minus a squared. They're especially useful for those. You don't necessarily have to have the square root on them, but because of the way the trig subs work and with the identities, when we make these specific trig subs, we will get perfect squares. And so when we have a square root over an expression of one of those forms, it's especially handy because the square root of a perfect square will simplify down very nicely. So the one that we just did is the one I have up here on the screen. And this reference sheet is linked in your Canvas course, so you can check that out and look at this. But the one that we just did, we had 4 minus x squared under a square root. So I picked x to be equal to 2 sine of theta, and my dx was 2 cosine of theta, d theta. And I made the substitutions. There was, of course, a restricted domain so that I could use that function, make sure it had an inverse. I made the substitutions. We ended up getting that perfect square. Things simplified down really nicely, and we drew a reference triangle in order to work our way backwards to get our function in terms of x at the end, because after we'd gone through that whole process, we had an integral in terms of theta, and I needed to get it back in terms of x. So this is if we have an integral with something of the form a squared minus x squared, especially if it has a square root of a squared minus x squared, this is the substitution we want to use. We want to let x be equal to a times the sine of theta. Now, I just wanted to mention down here at the bottom, I have added in, and I put it here in blue, we're using a sine of theta as our substitution, but we could very well have have used a cosine of theta as the substitution. The work would look a little different. The restriction would be a little different because for cosine to have an inverse function, the standard restriction is to restrict theta from 0 to pi. And then, of course, when we draw the triangle, it would look a little different, but we could absolutely use that substitution for roots of the form a squared minus x squared. Those will simplify down using an a cosine as well. All right, we do have 2 more substitutions on this strategy sheet, and I will show those briefly, and we're going to come back with another video to practice these. So those other 2 roots, if we use substitutions, if we have an a squared plus x squared, then the substitution that we would want to use is a tangent of theta. We restrict between negative pi over 2 and pi over 2, non-inclusive of those endpoints because of the domain of the tangent. And then that works out really nicely because of our trig substitution. When we make the trig substitution, we end up with a 1 plus tangent squared that will simplify out nicely to a secant squared. Take the square root, of course you get the absolute value, but on that restricted domain the secant will be positive, and our triangle will look like the triangle I have over here. Now if we use if we see a root of the form x squared minus a squared, or any expression of that form, x squared minus a squared, we can use a secant as our substitution. Now this one we do have a more interesting, shall I say, interesting restriction on the domain. Different books use different restrictions, but this is what our textbook is using. So we have this restriction, we let theta be between 0 to pi over 2 if x is greater than or equal to a, and between pi over 2 to pi if x is less than or equal to negative a. Make the substitution. Because of that restriction, when we take the absolute value, we do have to think about if the tangent is positive or negative when we take that absolute value. And so I just made this little note. A lot of times in our homework or in our work, you will see a note that says, that gives us a specific restriction on the domain so that we can use just the positive or just the negative. But sometimes we need to take a look at that and check that, and if it is not given, if we're not given a restriction on the domain that allows us to use just one piece of that, we might have to use a piecewise function. Okay, and then of course the triangle that corresponds. So those are the reference pages for this strategy, and now we're going to go ahead and practice a few more of these, and I'll go ahead and just put this up on the screen. So again, this is a very useful strategy. We do want to recognize which of the trig subs to use and what restriction on the domain allows us to use that, and then we can work our way through things. It's kind of fun because these problems, they end up, we end up making the substitution, and the problem, the integral almost gets bigger, and then it just nicely compacts down and things simplify, and we're able to integrate using some trig strategies for integration, and we end up finding our answer and using some back substitution out of a triangle.